Alright, and welcome to this week's video concepts. And in this piece of work we've already looked at energy, and I'm not going to put a video together for energy, at least not yet. I may do in the future, because it's not really the focus of what we're interested in this week. So the PowerPoint and the voiceover for the PowerPoint should be sufficient to get the understanding about endergonic and exergonic reactions. What I do want to talk about is twofold. First of all, I want to look at the role of a specialist group of proteins called enzymes. And then in following short video concepts, I then want to go on to look at specific chemical reactions which require enzymes, which occur in our cells, which contain mitochondria. And to an extent, ones that don't can do the first stage of it, and this is called cellular respiration. And I'll go through that in two stages. I'll do the first stage by itself, and then I'll do the next two stages in a separate video. So in this one, we want to look at enzymes, and so on the board here I put some of the main points of things that I want to talk about in enzymes. Now, what does an enzyme do? An enzyme is a facilitator. It helps and allows a reaction between two molecules or more to take place, which without the enzyme present would not take place. To use simple analogies, our cooking, and most of us know how to make a soup or something of that nature. And when we make a soup, we take water and we take ingredients, vegetables, meat, etc. and we put them together, and then to make the soup we put the heat on. And so the heat in this analogy is acting in the same way as an enzyme does in a cell. It changes the molecular structure of the vegetables and the meat, etc. in the boiling water into something which is now soup, which before was just water containing various bits of vegetable and meat. To do that, well, water boils in Fahrenheit. Water boils at 212 degrees Fahrenheit or 100 degrees centigrade. Now, you should already know that your cells cannot be heated to boiling point, or the boiling point of water, without them dying a long time before they get there. For example, in Fahrenheit, our cells are sitting around about 98.6 degrees, our body temperature. If we have a fever that runs above 105, 106 degrees Fahrenheit, we get into trouble. And if we get to 108 and above, we are getting to the point where we may not survive the process. And that's still over 90 degrees away from boiling point of water. So to get reactions to occur inside the cell, we can't change the temperature enough to add enough energy into the system to make the reactions take place. And this is where the enzymes come in. They offer an alternative route to get the reaction to take place, which doesn't require damaging levels of heat in the cell. An alternative way we could do it, if you wanted to play around with eggs, because I know you've already done that with your cell membrane transport, is you can take an egg, and of course you can crack it open, put it in a frying pan and fry it, and you see the clear albumin change to white and the egg yolk harden up. You could do the same in acid. You can put it in vinegar, just crack an egg into vinegar, leave it sit there for a few hours, and you'll see the albumin turn white. Now, why would it do that? Well, if we go back into our second week and think about acids, remember, acids are adding hydrogen ions to the system, and these hydrogen ions are interrupting or getting in there and causing changes, denaturation of the protein and the albumin, the egg white. And again, that's changing the structure just in the same way as the heat would be doing by adding extra energy. Once again, you can't do that in a cell, because to suddenly just turn the cell from a pH of about 7 to a pH of about 2, to make it very acidic, to make something change, would destroy much in the cytoplasm of the cell. So these two methods, changing the charge around the reactants or changing the energy level around the reactants, are not possible inside living cells. So an enzyme, the specialist protein, offers a safer or safe route to make these reactions occur. Now, what they are essentially doing is they're lowering the energy required to make the reaction take place. So what an enzyme does is it lowers the energy of activation, and the activation is of the reaction. So we can write that in short form as E of A, energy of activation, and we can graphically represent it. So without an enzyme, I'll just put here without enzyme, with enzyme. So we have our reactants on this side, we have our products on this side. Without an enzyme, the energy of activation is very high. You have to put in a lot of energy to create this over to here. But if we add an enzyme to the system, the energy required for the reaction to take place is drastically lowered. So much so that there's enough energy within the system to allow this to become changed and become the product. So keep in mind that enzymes are proteins, and that proteins' primary structure starts off their full structure, and then secondary, tertiary, and quaternary come in behind that. So secondary is the hydrogen bondings, the tertiary is all the ionics, the hydrogens, the covalents, disulfide bridge bonds, all of that. So they hold a specific shape. And this actually takes us to how enzymes get their job done. There's two mechanisms by which they actually physically do the job, but first of all I'm going to talk a little bit more about the energy of activation and how they lower it. And this is by removing the randomness of the process taking place. If we go back to when we were considering Brownian motion and the fact that all atoms jiggle and that makes things diffuse, if you remember that concept lecture, and of course if you don't, I encourage you to go back and read it again or listen to it again because it's an important concept. So if you've got a molecule here, it's got two parts to it, and it's both are atoms and they're jiggling about. So it's moving around in its environment. Now, for it to change, say to be broken into its component parts, there's no particular reason why at some random moment in time it's suddenly going to do that, and now you've got, you know, two independent parts moving. Something has to happen to it. So, what does happen to it? Well, if you're in a liquid, for example, or a gas, you've got these things moving around, and every so often they'll hit each other and move away again. And remember, that's what Brownian motion is doing with diffusion. They hit, they move away, the more things are in there, the more times they hit, the more they separate out from each other. So you can hit many times all over this molecule. So many collisions can take place. Nothing really changes, but 1 in a million hits it right there, and that breaks it. And suddenly we have our reaction. So that's random. You're just, you know, this could happen at any moment, but it happens so infrequently and so slowly that actual chemistry, there's not enough product to ever get anything done. What the enzyme does is it takes away this random motion and occasional collision with something else that causes the bond to be broken. The enzyme has binding sites for the molecule. So it has what we call the lock and key method. And the key is the molecule, the reactants, the lock being the enzyme itself. So instead of randomly moving around, maybe going to hit something, maybe not, and maybe hitting it at the right point, it is clamped on by the enzyme. So all that randomness is immediately removed. It's now fixed in place, right there, so things can be acted on and bonds can be broken. The second phase of that is the induced fit model. So I've graphically shown them here. Here's the enzyme, and here's the reactant. Now I haven't actually named them, so maybe I should go ahead and do that just for thoroughness. This is the enzyme, and this is the reactant. Oops. And then if I can, and I'm not sure I can, because my artwork is never that great, show you that the product fits in right there. So we started with the enzyme present, the reactant, they're now bound, so they become an enzyme. We can also call this a substrate. The problem with science is that we have words for everything, and we have multiple words, so let's put that in brackets, substrate, the thing that you put in. So this becomes known as the enzyme substrate complex. And as we have the enzyme substrate complex, that then causes a breakage in the bonds, and that releases the products. The enzyme is not changed, so it can go ahead and do it again. So one enzyme can set up millions of the same reaction, one after another, like a conveyor belt of products being produced. So it takes away the randomness by locking it in place, finding the substrate or reactant, locking it in place, and then breaking the bond and then releasing it. Then the enzyme goes ahead and does it again. The enzyme is specific only to one type of chemical reaction. It only has the binding site and the ability to change one particular substrate into one group of products or singular product. So the enzymes are very, very specific. So you have to have an enzyme for every reaction that you need an energy input in a cell to make it function. If you're missing an enzyme, then that reaction will not take place, or certainly not take place at a rate that is any use to you or your cell. The last concept I want to talk about is the induced fit. Once you've got it locked and loaded in here, and I'm showing you in this way, there's the binding site. Here again is the enzyme, which I will tag. So reactant substrate is the little blue line here, joined in on the enzyme. The last part is induced fit. Now induced fit is when it binds into this lock and key method, there is a slight change in the protein structure because you've just bound something which has charge on it, and it causes it to actually put, now if we go back to my cheap and cheerful pens here, once it gets locked in the enzyme, it puts it under a pressure. So bond strain, it takes energy to break the bond, and that's what the energy input is actually for. And so the enzyme, because it changes it, start again, enzyme's here, binds on, and then the enzyme gets changed because of the binding, and it puts strain on the bond. So there's very, very, very little energy required to cause that bond to break. So it's specific in that it's a lock and key. It implies or puts on an induced fit to put bond strain in place to break the desired bond, and that lowers the energy of activation to a point where the reaction proceeds really quite simply. The enzyme is not changed by it. It can do this again and again and again until the enzyme itself is deactivated from another system, or it runs out of substrate, etc. Now in the labs you'll look at that, and you'll look at the effective temperature, and you'll look at the effect of concentrations, etc., on the rate of the reaction using a simple catalase and hydrogen peroxide experiment, and you will need to provide the potatoes and provide the hydrogen peroxide, I'm sorry to say. Alright, well, this is basically the important take-home information regarding how enzymes act. There's much more information contained in the PowerPoint, which isn't need-to-know information, it's all there. And I have a voiceover for that, so this is what you absolutely have to take away. What's in there is what I would really like you to be able to understand. So good luck with that, and when we come back in the next talk, we'll start talking about cellular respiration.